So Math 3A section 4.1, maximum minimum values. Before we do this, we're gonna go over some quick review of derivatives. Here we have sine, it looks like sine u. So the formula to find the derivative of sine u is u prime cosine u. So basically the derivative of ln of this. And the derivative of natural log of u, it's u prime over u. U prime over u. So y prime would be the derivative of natural log of x times cosine itself. Then y prime equals, the derivative of this is 1 over x cosine natural log of x. For number 2, if we have recall log u base a, then y prime, it's u prime over u times 1 over a, isn't it? 1 over natural log of a. So y prime is 2x over itself times 1 over natural log of the base. Here we do quotient rule. The derivative of the top times the bottom one minus the top times the derivative of the bottom one. That's quotient rule. Quotient rule. Then y prime would be 2x times x plus 3 minus x squared minus 1 times 1, all divided by x plus 3 squared. So what's y prime? Y prime is 2x squared plus 6x minus x squared plus 1 all over x plus 3 squared. So that gives me x squared plus 6x plus 1 all divided by x plus 3 squared. That's y prime. For number 4, we use product rule. The derivative of the first one times the second one plus the first one times the derivative of the second one. So y prime is 3x squared times this plus x cubed times 2x times itself. Usually we prefer to factor things out, like x squared out, e to the x squared out. That would leave 3 plus 2x squared, like that. So after we reviewed a little bit about derivatives, we may move on to cover section 4.1, talks about the minimum and maximum values. So either they're gonna give you a function f of x, or maybe let's say a graph like this. So the question is how to find the maximum / minimum values of such a function or graph. To do that, we're gonna get something called those minimum maximum. They classify them as either absolute max or min. Some people call it global, depending on the book, or local min or max. Some people call it relative. Now, after we find the x value corresponding to min or max, then the max and min values, of f are called extreme values of f. Note, these extreme value, or some people say extremum, the singular is extrema, the singular is extremum. Every time you see extrema or extremum, or means min and max. So we're going to look at how to find the local min and max for a given function. That's the first thing. So local min slash max of f over a specific interval. So it is over a certain neighborhood. Graphically, you will get the better idea when I do the graph. So this is the local min or relative min. So that's the minimum value within a certain neighborhood. This part top one, that's local max. So that's the maximum point the graph can reach over that interval. This is local min. So again, local min occur at these kind of points. Local max, they occur at the top. So in this case, for this second graph, there's no local min. There's only local max. For the first graph, no local max. Only local min for this specific graph. So that's for the local. Now for the absolute min or max, how do you find them out? So the absolute min slash max over the entire domain of a function or a graph. Note, it can be, so the absolute min or max, it can be at the endpoints. Points of the graph. So for example, if we have something like this, let's call this point A, B, C, D. Look at A. Point A is the highest point the graph can reach. So A is considered absolute max. B is the lowest point the graph can reach. It's an absolute min. And guess what? And also, it is a local min, because it's within this neighborhood. That's the lowest point. How about C? C is only local max. And D, nothing. You cannot have local min or max at the endpoints. So I'm gonna give you this one. List if there's any min, local max, absolute min, absolute max. As you can see, the first one has neither local min or local max. Same thing, neither local absolute min or absolute max. Next one. Look at A. A is the highest point the graph can reach. So A is an absolute max. B is the lowest point the graph can reach. So that's an absolute min or global min. Now we look inside. This one here, D, is a local min. C is a local max. B
Professor.
is, wait, let me finish. B is a local min. So now, again, the highest point the graph can reach is A. So A is the absolute max. The lowest point the graph can reach is B. So that's absolute min. So I'm done with the absolute part. Now for the local min and max, you do not look at the endpoints, you look inside. So don't look at E or A, but look at the other points. D, it's at a local min. C is a local max. B is a local min. You can have more than one local min or one local max. And that local min at B is the same as an absolute min, which is okay. It can be both at the same time. So now we introduce a theorem here. It's called the extreme value theorem. The extreme value theorem says if f is continuous on a closed interval, AB, then f attains absolute min or absolute max value, call it f of c, and an absolute min value f of d in the interval AB. X, Y. So I'm drawing some samples. Let's look at this one. These are just applications to this theorem. Very important to look at the conditions of the theorem. The theorem works only if the function f is continuous on a closed interval, closed like this, like it has a bracket. Then if that's the case, if it's continuous or closed interval, it must attain an absolute max and absolute min values. That's what the theorem is saying. So for the first case here, as you can see, it's continuous. There's no holes, there's no jumps. So this is the absolute min. This is the absolute max, right? So it must attain absolute min, absolute max. Here, it's continuous, right? On a closed interval, this is the absolute min. This is the absolute max. Next one is continuous. You can also find maybe this is the absolute min, this is the absolute max. Next one. What do you think about the next one? This one, not continuous, right? Not continuous. So we say it fails the extreme value theorem. Conditions, right, about continuity. What about the next one? Think about it. It's a continuous function, but what? Continuous, but not a closed interval. As you can see, it's the arrows means it goes forever. That's what this means. The arrows means goes forever. Another theorem here to state is called Fermat's theorem. Fermat's theorem said if f has a local min or max at x equals c, then f prime at c is 0 or f prime at c does not exist. So f prime at c equals 0 means, so what is f prime? F prime at c is the slope of the tangent line. Same thing here, so slope of tangent line. So the slope of tangent line is 0, means like this, you're gonna have a horizontal tangent line, or it could be like this. That means that's when f prime at c equals 0. That's when the slope is 0. And does not exist, that's when you have maybe like a vertical tangent like this. You have something like that. That's when the derivative does not exist. So it says if f has a local min or max at the point c, then one of these has to happen. So if you look at this graph, let's say this point is A, this point is B, and this is F. So what do you notice? At A, there's a horizontal tangent, so f prime at A is 0. At B, there's another horizontal tangent, so f prime at B is 0. So notice at x equals A, f has a local max. At x equals b, f has a local min, or vice versa. At a there's a local max, so f prime at a is 0. F has a local min at b, so f prime at b is 0. So again, we can say that f prime of c equals 0 or does not exist provides all possibilities where f might have local extreme values. Extreme means min or max. So instead of keep writing min and max, we say extreme values. I'm going to draw a graph for the function f. Call this x1. This is x2. So what do you think about this. Try to fill this up. So f prime at x equal x1, it's 0, and the other one does not exist. Note, x1 and x2 are called critical numbers. x1, x2 are called critical numbers. So that motivates us to introduce a definition. A critical number of a function, critical number of a function f is a number c in the domain of f for which f prime at c is 0 or f prime at c does not exist. So any x value that will make f prime at c 0 or does not exist, we call it a critical number. How about if it's not, the function is not given as a graph? Okay, so what do we do here? Find any critical numbers for the following functions. Let's say f of x is x cubed minus 6x squared plus 9x plus 2. We need to find the derivative, which is 3x squared minus 12x plus 9. When is this 0 or does not exist? So this will always exist. So when is it 0? We can divide everything by 3, then factor x minus 3x minus 1 equals to 0. So that would give me x equals 3, x equals 1. So the numbers 1 and 3 are critical numbers. So again, in this kind of specific function, the derivative will always exist. I'm going to pick another function now, this function. Find the critical numbers. Find the critical numbers. Note here, the critical numbers must fall in the domain of the function. They must fall in the domain of the function. Now, if we look at this one here, what do we need to do? We need to find y prime. How do you find y prime? Derivative of the top times the bottom one minus the top times the derivative of the bottom one over the bottom one square. So you get negative 1 over x minus 2 square. This will not equal 0. I mean, you can't have negative. If you cross multiply, you get negative 1 equals 0. So you can't set y prime equals 0. How about, so y prime cannot be 0. How about y prime does not exist? Well, it does not exist when the denominator is 0. So y prime does not exist when y prime is when the denominator is 0. So that tells me x equals 2. But you have to watch carefully here. That's a tricky thing. Notice if you go back to the original function, you will notice the domain of this function as a domain. It's all real numbers except 2. You can't have 2. 2 is not in the domain. And since I got x equals 2 when the function or the derivative does not exist, we can say but x equals 2 is not in the domain of the given function, domain of f, then we can say x equal to 2 is not a critical number because it's not in the domain. I have another example. Y equals f x equals x minus 2 to the 2/3 over x. Always we need to find y prime and see when is y prime 0 if it's possible, and when is it does not exist if possible. So try finding the derivative for this function, please. So we're gonna find the derivative for this function using quotient rule. So y prime equals the bottom one times the derivative of the top 2/3 x minus 2. Subtract 1 from 2/3 becomes negative 1/3 minus the derivative of the bottom one times the top one over the bottom one square. So y prime is 2 over 3 x minus 2 to the 1/3 minus x minus 2 to the 2/3 over 1 x squared over 1. Now the least common denominator, this is how I simplify those complex fractions. I look at the least common denominator for each of the fractions and I see it's 3 times x minus 2 to the 1/3. So we multiply by 3 times x minus 2 to the 1/3, 3 times x minus 2 to the 1/3, 3 times x minus 2 to the 1/3. Then y prime equals, these cancel out. You get 2 minus 3 times x minus 2. 2/3 plus 1/3 is 1, and the denominator stays the same. Y prime equals 2 minus 3x plus 6 over 3x squared times x minus 2 to the 1/3. So the final answer would be I forgot an x here next to the 2, so that's a 2x. 6 minus x over 3x squared times x minus 2 to the 1/3. Okay, now we continue. We're trying to find the critical numbers. So we're going to see when is f prime of x is 0. So f prime of x is 0 when the top is 0, when x is 6. Make sure 6 is in the denominator domain. Is it in the domain of this? Yes. The domain is basically here. You can make sure it's all real numbers except 0. So any value we get for critical numbers, okay, except 0. So f prime equals 0 when x is 6, so that's okay. So this is one of the critical numbers. And f prime of x does not exist when the denominator is not 0. When the denominator is 0. And denominator 0 when x squared is 0, and when this is 0. So when x is 0 or x is 2. 2 is fine, so this is also a critical number. But guess what? It's not 0. 0 doesn't work because it's not in the domain. So this one not in the domain. Remember we said domain is all real numbers except 0. So this function has two critical numbers. One is 6 and the other one is 2. Now, earlier someone asked, how about if they give us a function like the equation with no graph? Do I have to graph it? The answer is no. What we need to do is we answer this question: how to locate extreme values. Extreme values. In this case, I'm talking about the absolute one, absolute min and max. How do we locate them if they give me a function? So let's say let f be continuous over a closed interval AB, then the absolute min or max and max values of f are the smallest and largest values respectively found using what? Part 1, values of f at the critical numbers. In the open interval AB. And 2, we find f of A and f of B at the endpoints. And whichever is give us the highest value, that would be the absolute max. Whichever one gives me the lowest value, that would be the absolute min. In summary, we are going to see here how to locate extreme value, like for the absolute min and max, if the graph is not given, but only the function is given. So how do we do that? To do that, we find first the critical numbers, and then we evaluate the function at those critical numbers. Plus, we evaluate the function at the endpoints of the closed interval. And then whichever gives us the highest value, that would be the absolute max. Whichever gives me the lowest value would be the absolute min. So this, to reinforce this concept, find the absolute min / max values of, let's say, y equals f of x. This function, we did give you this function earlier when we asked you to find the critical numbers. Here I'm gonna just add on the interval 0 to 2. So the numbers you work with, they must fall on that interval. So what we did, we found earlier that x equals 1 and x equals 3 are critical numbers. But notice 3 is outside this. It's outside the domain, or that interval 0 to 2. So what do we do in this case? Since they are outside, so what do I need to do is evaluate the function at the critical numbers, and then we also evaluate the function at the endpoints. The endpoints are 0 and 2. 0 and 2. So what is f of 1? F of 1 is 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. I found this to be 6. F of 3, again, you can't evaluate it, does not fall, not in the interval 0 to 2. F of 0 is 2. F of 2 I found to be 4. Just substitute it in. Which one is the highest? This is the max. This is the maximum value. This is the lowest value, the minimum. So the function has, f has absolute maximum at 1, 6, when x is 1, y 6, and f has absolute minimum at 0, 2. 0, 2. We are going to do the same for this function, the one we found its critical values earlier. I'm going to just add an interval 1 to 10. We found earlier f prime of x in a previous example. It found to be negative x plus 6 over 3x squared times x minus 2 to the 1/3. From here we got that x equals 2 and x equals 6 are the critical numbers. And we found f, we can find now f of 2, f of 6, and the endpoints of the interval, f of 1 and f of 10. So f of 2, if you substitute the 2 in, what do we get? For the first one, I got this 0. This one I got about 0.42. The f of 1 is 1, and this is about 0.4. So notice this is the lowest one, so that's the absolute min. That's the absolute min. And this is the highest one, so that's the absolute max. Any questions up to this point? This is what this section is about: how to find min, max, absolute min, absolute max, local min, local max, critical numbers.